about thinking in 4 dimensions here. So that's hard for anyone to do, if not impossible. So what we've done essentially is make 2-dimensional mathematical analogs of these things. So this isn't really what the universe looks like, but if you suppress 1 dimension, we're going to talk kind of about the properties of the things you would see. So there are 3 possibilities. The first one is that the universe has a closed geometry, which means there's enough matter in the universe to actually warp it into a positive curvature. And that looks a whole lot like the surface of a sphere. In reality, it would be the surface of what they call a 3-sphere. Mathematicians would call it 3-sphere. But we're going to look at it in terms of a 2-sphere because Apple's keynote doesn't do 4 dimensions yet. Okay, so in that case, we draw big triangles on these things because that's the way you would tell if you were in curved space. If you take your geometry from Euclid that you learned in 9th grade or whenever we learned geometry, we know that triangles, interior angles sum to 180 degrees. That's only because space is flat. In a positively curved space, those triangles would actually have larger angles between them, and you'd have more than 180 degrees in triangles. This is one way you can measure if you're in a curved space-time or not. The other option is that space is actually negatively curved. In this case, there's less mass than it would take to have what we would call a flat universe. And in this case, the triangles would actually, the triangles' angles would be pinched, and they'd have less than 180 degrees. And of course, we return to our Meisen-friendly Euclidean case here where we're exactly flat. Now, each of these shapes is actually tied to the destiny of the universe, or it was in 1995 anyway. But if you take the expanding universe model according to general relativity, you find that the closed universe has enough matter in it that it can actually expand for a while and then turn around and then big crunch. And it could potentially do this over and over and over again. We can have a cyclic kind of effect here. The flat universe will actually expand forever, but at an infinite time in the future, it will actually slow down to 0. So it's the critical case where it's just about collapsing or recollapsing or expanding forever. And then, of course, the open universe doesn't have enough mass in it, and the initial expansion just takes it off forever and expands forever. Now, the interesting thing to note that I'm going to bring up that is going to be important later is that this flat universe case is actually really unstable. In other words, if the universe has any initial curvature at all, the end result will be more curvature. So if it's slightly curved away from this case early in the universe, it should be much more curved now. So we wouldn't expect to find a flat universe. Right? That would have to be a really finely tuned initial condition. So once this is all established, people, physicists have a lot to do, have a lot to think about, right? But some pretty smart people in the 40s actually thought about this, and they said, well, if the universe is expanding, well, there's matter in that, and our other physics of thermodynamics and stuff tells us that if we're expanding, we're cooling, right? So they said, all right, well, the universe must be cooling. And then, of course, the next thing was the thought experiment of running the universe backwards. Well, in that case, it's contracting and heating. Well, eventually, the universe gets to the point where all the stuff in it's hot enough to ionize, right? So the universe as a whole could be in the past, could have been as hot as the sun, right? A very opaque, hot universe that's ionized. So then we run the clock forward again, and we realize that there's this transition between opaque and transparent in which all of the photons from the black body spectrum that we would expect for a sun-like temperature would then free stream through space, and we should be able to see this radiation today. The radiation would be quite redshifted, and they did a calculation that says that basically this thousands of Kelvin initial black body would now look like 5 kelvins in the sky. So there should be this afterglow, this microwave radiation. In the 60s, people started looking for this. A couple guys from Princeton and other places started looking for something they called the cosmic microwave background. This is a prediction of the Big Bang theory, one of the first ones we had, other than the sort of nascent prediction of the expanding universe, which Hubble was able to actually show. They didn't find it because these guys did. In 1963, two guys from Bell Labs in Homedale, New Jersey, Arno Penzias and Robert Wilson, who were excellent experimentalists, by the way, were pointing their communications disk to the sky to use it in astronomical research. And as always, they were astronomers. They were always worried about the noise in their system because astronomers always deal with extremely low signals. They did everything they could to get rid of this excess noise. They tried, looking at the side lobes, for those of you who do electrical engineering. They tried cleaning bird droppings off of the instrument. Finally, they were just like, we can't get rid of this signal, and it turns out it was about 5 Kelvin. They were talking with someone who was related to Princeton, and they were complaining about this problem, and the guy's jaw hit the floor because he knew exactly what they had done. They provided the first experimental evidence for the Big Bang. According to legend, when Peebles got the call at Princeton, he said he got off the phone after a very quiet phone call and announced to his team that, boys, we've been scooped. The other cool thing about this that I always like to point out is that this is the title of the paper that they published: A Measurement of Excess Antenna Temperature at 4080 Megacycles per Second in the days before the unit hertz. The cool thing about this is that this is the most understated paper title I've ever seen, because what they really did was really provide tangible evidence for the Big Bang. You know, today that would have been like exclamation point in capital letters and everything, right? But they won the Nobel Prize in Physics for this in 1978. In addition to kicking off half a century's worth of cosmic microwave background exploration. The cosmic microwave background is actually one of the best tools we have now of learning about the very early universe. The next step in that, of course, was 1994, when the Cosmic Background Explorer, led by John Mather and George Smoot, and this was actually led out of Goddard Space Flight Center, which was kind of a prideful thing for me. They discovered that the spectrum of the cosmic microwave background was exactly what you would have expected. They did detailed measurements of the spectrum, and it fit the Planck spectrum of a black body exactly. And so they were able to measure the temperature of the cosmic microwave background. It wasn't about 5 Kelvin anymore. It was 2.725 Kelvin, and basically uniform everywhere across the sky. So this was even more evidence for the Big Bang. And in addition to that, we're starting to get to the era where we're actually measuring real numbers to significant figures. The other thing that this experiment did that was cited in the Nobel Prize citation was they discovered that even though it's uniform to about 1 part in 100,000 across the sky, there's a small anisotropy in the background. This was actually expected because you need a tiny little bit of anisotropy in order to form galaxies and stars and planets later in the universe's history. So they actually did discover that as well. And I can show that a little bit more detail here. So basically, you've got in the early universe is mostly homogeneous and isotropic, as you can see up here in the COBE map. But there's little tiny density perturbations, we call them. And what happens to those over the course of cosmic history in about 500 million years is the dense regions pull in matter from the less dense regions and become denser and denser. And eventually, they become so dense they can form the first stars and the first galaxies. And that's basically what leads to the structure formation in the later universe. So this was something that was expected, predicted, and was borne out by the observations. So what to do next after that? Well, it turns out the details of the anisotropy in the cosmic microwave background are extremely important and can tell us a lot about the physics. But COBE wasn't fine-tuned enough. It didn't have enough angular resolution to actually to explore that in any kind of detail. So the next thing we did, or cosmologists did, was to launch another probe, which basically effectively put a pair of glasses on COBE. It had finer resolution and had more sensitive detectors, and was able to bring that picture in a little bit more focus. So this is one of the most famous pictures in astronomy these days. This is a baby picture of our universe. This light is the oldest light in the universe that we can possibly take a picture of. It comes from about 400,000 years after the Big Bang, which is about 13.7 billion years in the past. And this is a more detailed picture of what the universe looked like at that early age with, again, you can see the anisotropy and the scale of the anisotropy due to these over-densities and under-densities in the universe. However, the Big Bang model doesn't predict exactly what this should look like. You can't ask the question, if I point here, what should the flux be? Or here, what should the flux be? The statistics of this are actually what are important. So cosmologists will look at this picture like this. This is basically for those of you who are interested, this is the two-dimensional spherical Fourier transform of that map. And you can see there's these resonances. And these resonances actually capture all the details of the physics that went on and allow you to measure the parameters that go into the Big Bang model. And I can kind of show you some of the basic features. People get sort of an intuitive feel of this. And the location of this peak, for example, tells you how flat the universe is. The height of this peak tells you how many baryons are in the universe, how much normal matter is in the universe. This peak tells you something about the dark matter. And the stuff out here is actually stuff that never had causal contact with each other. This tells you exactly about the initial conditions of the universe. It turns out, I mentioned before that flatness was something, the universe's shape tells you it was very unlikely that they were going to find a flat universe, right? Turns out they actually found exactly a flat universe, or at least exact enough within the measurement error. So that's kind of one of the mysteries that's laying out there, that we have this unstable condition in the universe of flatness, but yet 13.7 billion years, it's still, the universe is flat. So what we're actually getting out of this in terms of cosmologists is 6 numbers. This red curve is parameterized by these 6 numbers, which capture our information, which go into the model and capture our information about what the universe is doing. And it does pretty well, right? I mean, the data here are the black points, and the model goes through most of them, right? So we've really come a long way in understanding the physical mechanisms, at least, you know, from the first 3 minutes on, out to our current observations of the universe. One more piece of this puzzle, of course, is continuation of Hubble's work. Remember, Hubble plotted, it's right here, recession velocity versus distance, right? And he basically looked at the very local universe, because that's what he was capable of looking at, and he found that there was a linear relationship. Well, in 1999, and this was 4 years after I entered graduate school, the amazing discovery was made that if you go out far enough, you'd expect the universe to be sort of decelerating in time, because we've matter dominated and the matter is slowing down the acceleration. But in fact, the curve went the other way and actually started to go into the accelerated universe side. So this was surprising, to say the least. But it brings back the specter of Einstein's cosmological constant. If you had some kind of cosmological constant or similar thing out here in this equation, it would do exactly that. We've dubbed this dark energy because we don't know what else to call it. And so Einstein's greatest blunder ended up being something much more prescient than he could have probably imagined at the time. So here we are, the universe as it is today, a nice big pie chart. 4% of the stuff in the universe, the good news is 4% of the stuff in the universe, we really know what it is. It's normal matter, it's planets, it's stars, it's us. We got it. We got that wrapped up. 22% of the universe is dark matter. This is stuff that interacts gravitationally, can have a big gravitational effect, but doesn't seem to interact with light at all. So that's kind of okay to imagine. We can imagine maybe there's something in the particle physicists haven't found yet that could do this. Some neutral particle in the particle zoo. However, there's 74% of the universe that we really have no idea what it is. The only thing we know about it is that it causes the universe to accelerate, to push the universe apart faster. So that leaves us with our open questions. There's one of course, I mentioned that the CMB the cosmic microwave background was very uniform across the sky. In the standard Big Bang cosmology, there was no way for opposite points in the sky to ever have talked to each other. They would have never been in causal contact. This is known as the horizon problem. Of course, I mentioned before, why is the universe so flat? Flatness is a very non-stable condition. This leads to something that we've dubbed the flatness problem. And then, of course, why is the universe expanding? I kind of biased my talk towards the expanding universe, but Lemaitre and Friedman equations don't care. The universe could also be contracting. And then, of course, where does the structure that we know has to be there in order to form, the anisotropy that we know has to be there to form the structure, where did that come from? So one possible answer to this is inflation. This was an idea that Alan Guth came up with in 1981 that says basically in the very early universe, the universe expanded by a factor of 10 to the 30 in 10 to the minus 32 seconds. And I wrote this for my own edification to kind of give an idea of how big that actually is. The physical motivation for this actually lies in quantum field theory. And basically what this is trying to do is provide a causal mechanism to set up the initial conditions of the Big Bang model. In other words, our current cosmology as we understand it will take a set of initial conditions and very faithfully run that through and capture all the physical processes and tell you why things are the way they are today. But before that window in